Jai Hind to all. Myself Uma Sharma, Assistant Professor in EC Department, Ajay Kumar Garg Engineering College. Welcome to the lecture series of Analog Circuits KEC 402. The topic of this lecture is oscillators. This is very important in the analog circuit course. This topic is from Unit 3. So, moving towards the basic concept of oscillator, first we should know the concept of feedback. So, when we talk about any system, there may be two categories. One is open loop system and another is closed loop system. So, when we talk about the open loop system, that means there is no feedback involved. There is no feedback. But in case of closed loop circuits, there may be two types of feedbacks, negative feedback or positive feedback. So, in electronics, generally we use both the feedbacks, negative feedback and positive feedback, and based on the feedback, the application of analog circuits is classified into two different categories. Like when we use negative feedback, then or I can say we use negative feedback generally in the amplifier circuits. The applications of any analog circuit as an amplifier, we use negative feedback over there. Amplifier may be your BJT, maybe your MOSFET, maybe your op-amp, any circuit which can amplify this any input signal comes under the category of amplifier. And in amplifier, generally we use negative feedback, whereas in case of oscillators, this is another domain of application in analog circuits. This is positive feedback. So, in oscillators, we use positive feedback. So, the feedback is a phenomena of feeding a portion of output signal back to the input circuit, and the effect of this portion of the output at the input node definitely used to control the working of the circuit. So, when we use negative feedback, this is having some effect on the output when we compare it with the open loop configuration. When we use positive feedback, then also it is having some impact on the performance of the circuit that we will see in this lecture. So, first we will discuss the negative feedback. This negative feedback is also known as the degenerative feedback. So, in negative feedback, the feedback signal, that may be the voltage or current. The feedback signal may be voltage or current. There are only two signals, two types of signal at the input. So, when we talk about the negative feedback, when the feedback energy is out of phase with the input signal, that means it is opposing it. So, that is known as negative feedback. Definitely, the negative feedback reduces the gain of the amplifier. As I have already told you, the amplifier uses the negative feedback, but the impact is that reduce the gain of the amplifier. It also reduces the distortion, noise and instability. That's why we use negative feedback in the amplifier, because we want a stable amplifier on which the effect of distortion is noise is very less. Whereas this feedback increase the bandwidth and improve the input and output impedances. In Unit 2, in the same course, we have studied the feedback amplifiers, where we have designed the 4 type of amplifiers using the negative feedback, and we have seen that there is a improvement in the bandwidth and input output impedances. For example, if we talk about the voltage amplifier, so in voltage amplifier, the effect of negative feedback is that here in the voltage amplifier, the gain reduces by some factor that we will see in the lecture, but the bandwidth increases, input impedance increases and output impedance decreases. So, that is very useful in the amplifier circuit. So, at the small reduction in the gain, we can use negative feedback to enhance the performance of the amplifier. So, here this is the circuit for feedback amplifier. Here the amplifier is connected. This is the simple amplifier, and another network is used in the feedback circuit, which is known as feedback network. and here you can see that a sine wave is applied at the input side and the output we are getting 180-degree phase reversal. So that we can get using BJT. This amplifier may be made up of BJT, MOS or op-amp. So if there is a 180-degree phase shift is introduced by this amplifier, then this signal, the portion of this signal goes to the feedback network. Here this is the output. The output behaves like an input signal to this feedback network, and this feedback network produces another signal which is known as VF, feedback signal, feedback voltage. If the phase shift introduced by this feedback network is 0, so that means the VF is in the phase of output signal and definitely out of phase with the input signal. So if we add this VF with V in, definitely there is a minus sign over there because both the signals are out of phase. So this is the concept for negative feedback. If there is a shift of 180-degree phase in between input and output, then the feedback is known as negative feedback. In positive feedback, which is also known as regenerative feedback, this is the another name for positive feedback. So in positive feedback, the feedback energy, which may be in the term of voltage or current, is in phase with the input signal. That means it adds to the input signal. So feedback, positive feedback increases the gain definitely because the nature is positive. So definitely it will increase the gain. Also it increases the distortion, noise and the instability. So in amplifier it is not required, but when we want to generate the oscillation, when we want to generate the waveforms, so in that case we can use this concept of positive feedback. So the concept of positive feedback can also be used in the circuit, and these type of circuits are known as oscillators. So in amplifier, because of these disadvantage, we cannot use this positive feedback. So just have a look how to add the signal, two signal in positive feedback. So this is the input signal, same as we have taken in the case of negative feedback. Here the again amplifier introduces 180-degree phase shift. So now if we want to add two signals, so that means another 180-degree phase shift is produced by the feedback network, and this feedback network is made up of R, L and C. This is the purely passive network. This feedback network is purely passive network, and using the combination of R, L and C, we can introduce this phase shift 180-degree very easily. So now you can see that the signal VF, which is a feedback voltage signal, that is in phase with the input signal. So definitely if we add these two signal over here, input and feedback, so there is plus sign. I hope you got the concept. So in the previous figure, because we are talking about oscillator over here, so we will use the positive feedback, the second diagram. So in that figure, the gain of amplifier is represented by A, the gain of this amplifier. This gain is represented by A, and the gain of this network is represented by beta. So this gain of feedback network is represented by beta. So V output can be given by A times of input signal, which is at the input of amplifier, whereas VF, which is the feedback voltage signal, and that is the multiplication of gain of the feedback network and the input to that feedback network. So the input to this feedback network is V naught. So the VF can be given as beta into V naught, whereas V input is equals to V input. This is the input at amplifier. So input at amplifier can be given as Vs, source signal, plus Vf, because positive sign we have seen that it is due to the positive feedback. So that can be Vs plus beta V naught. where beta is represented as gain of the feedback network, and that can be given by Vf upon V naught, because Vf is the output for the feedback network, and this is known as feedback ratio or the feedback fraction. So here you can see that the V output can be given as A into input signal at the amplifier, and the input at the amplifier is represented by Vs plus beta V naught, as we have seen in the previous slide. And if we solve this equation, then we will get V output upon Vs is equals to 1 upon, means A upon 1 minus A beta. If I derive this expression for the negative feedback, then this minus sign will become the plus sign. So for negative feedback system, the VO by Vs can be given by A upon 1 plus A beta. This is for negative feedback. So directly it is visible from both the expressions. So here gain reduces by this factor, whereas in case of this expression, the gain increases by this factor. So the gain of feedback amplifier is represented by AF. This is the overall gain with the feedback. If I talk about A, this A is open loop gain. This A is nothing, open loop gain. So just have a look to the difference between positive and negative feedback. So from both the diagram, it is clear that the feedback energy is out of phase with the input signal in negative feedback, whereas in phase with the input signal in positive feedback. Definitely that reduces the gain in case of negative amplifier, and we have seen from the expression the gain increases in case of positive feedback. The gain stability increases in case of negative feedback with the same factor 1 plus A beta, whereas the gain stability decreases in case of the positive feedback with the factor 1 minus A beta. Similarly, noise and the distortion decreases in the negative feedback, whereas noise and the distortion increases in the positive feedback. It increases the bandwidth, whereas the positive feedback decreases the bandwidth. So negative feedback can be used in the amplifier circuits, whereas the positive feedback can be used in the oscillators. So oscillators, if I define oscillator, oscillator is a circuit by which we can produce the oscillation at the output. So using oscillator, we can design a sine wave generator, a square wave generator, triangular wave generator. So oscillators are also known as waveform generator. So using oscillator, we can design a circuit, or the oscillator or the circuit by which we can produce a waveform of a specific frequency. But to produce that specific frequency, there are some certain conditions that we have to follow, and these conditions are known as the condition for sustained oscillation. And this criteria, this criteria is given by the scientist Barkhausen, and the criteria is known as Barkhausen criteria of oscillation. So the first condition for the oscillation is that A beta should be equals to 1, where A is the gain of amplifier, whereas beta is the gain of feedback network. If I multiply both these gain of the amplifier and the feedback network, that will, if this will equals to 1, then the sustained oscillations can be produced. This is the first condition to produce the sustained oscillation. And the second condition, because we want that the feedback signal and the input signal must be in the same phase. So either there is a 0 degree of phase shift, or it should be 360 degree of phase shift. If these two conditions are satisfied, then only we can produce the oscillation in the using the oscillator. So these are the condition for sustained oscillation. So by using this criteria, we can even find the value of different transistor parameters like gain, which is required to setting the oscillation, because we have to meet this condition. So we have to find out the parameters of the amplifier. We have to design the amplifier such that that comes A, that produce the A like that, then A beta will become 1. So to produce this A beta equals to 1, we require to rearrange the circuit. So based on the feedback network used in the designing of oscillator circuit, the oscillators can be categorized basically into two categories. One is harmonic oscillator, second one is the relaxation oscillator. So the harmonic oscillator are also known as linear oscillation oscillator, and relaxation oscillators are known as non-linear oscillators. Harmonic oscillators are also known as sinusoidal oscillator. Generally they are used to produce the sine wave. As it is written over here, in harmonic oscillator, energy flow is always from the active component to the passive component, and the frequency of oscillation is decided by the feedback path only. So in harmonic oscillator we can produce sine wave. So these are known as sine wave generators, whereas in case of relaxation oscillator, the energy is exchanged between the active and the passive component, and the frequency of oscillation is determined by the charging and discharging of the these passive components like capacitor. And further, using the relaxation oscillator, we can produce the different type of waveforms like triangular wave, square wave, and many more. So mainly the harmonic oscillator is categorized into these three categories: RC oscillator, LC oscillator, and the crystal oscillator. In RC oscillator, again there are two type of oscillators. One is known as Wien bridge oscillator, second one is known as the RC phase shift oscillator. In case of RC oscillator, the concept is that the feedback network is made up of R and C only, whereas in case of LC oscillator, the feedback network is made up of L and C. The concept of crystal oscillator is different from RC and LC oscillator. Here we use the crystal in place of passive component. So the category is based on the feedback network. So again I am repeating, if the feedback network is made up of R and C only, then the category is known as RC oscillator. If the feedback network is made up of L and C only, then the this is known as LC oscillator, and the feedback network is made up of crystal or quartz crystal, then it is known as crystal oscillator. So first we will see the RC oscillator, and the first type of RC oscillator is known as Wien bridge oscillator. So this is a type of phase shift oscillator again, because here we will introduce the phase shift using the feedback network. So here in the feedback we will use the combination of R and C. So they in Wien bridge oscillator, there are two arms which are purely passive. So one is made up of R and C connected in series, and another is made up of R and C which are connected in parallel. Basically the Wien bridge oscillator is made up of this Wien bridge network. That's why the name is Wien bridge network. The Wien is the name of scientist as well. So this Wien bridge network is used to design the oscillator. So in feedback there are four components: R1C1, R2C2, where R1C1 are connected in series fashion, and in this situation this R1C1 is representing a high pass response, or high pass connection is to design a high pass filter, whereas when R and C are connected in parallel fashion, this is equivalent to the low pass filter. So when we connect this network R1C1 and R2C2 in the feedback of the amplifier, then this circuit will make a Wien bridge oscillator. So in this circuit at high frequency, the reactance of the capacitor C1 and C2 will be much less, because the voltage VO will become 0 at R2 will be shorted. Next, at low frequency, the reactance of the capacitor C1, C2 will be very high. That's why this is the combination of low pass and high pass and low pass. However, in this case, the output voltage VO will remain at 0 only, as the capacitor C1 would be acting as an open circuit. This kind of behavior exhibited by the Wien bridge network make it this circuit like a lead lag circuit in case of low and high frequency respectively. So this is the circuit for Wien bridge oscillator. Here you can see that the same circuit which I have explained in the previous slide, RC connected in series and RC connected in parallel. So this is basically feedback, and this feedback is connected at the positive terminal of this operational amplifier, and at the negative node of this op amp, this R input and RF is connected. So the op amp with a gain of A is used to design the amplifier in this circuit, and the feedback network is made up of R and C. This is made up of R and C. So in this circuit there is no input. The basic concept of oscillator says that without the application of any input, the oscillator can produce the output because of positive feedback concept. So if we apply positive feedback, then a very small noise signal can be generate very high value at the output. So in case of oscillator, in place of input, at the first cycle we use noise as an input signal, and definitely in oscillators there is no need to apply any external input. This is the beauty of the circuit. So here you can see that there is no external input connected to the operational amplifier, only we have connected the feedback network at the positive node. So I hope you understand. If this feedback is connected at the non-inverting node, so this amplifier is non-inverting amplifier because inverting terminal is grounded. So this is non-inverting amplifier. So now let's see how we can derive the expression for the Wien bridge oscillator using this circuit. So we can calculate the voltage at this node, and this is represented by Vf. If we can calculate the value of Vf in term of V output, then we can calculate the value of beta, because beta equals to Vf upon V output. And once we calculate the beta, just by using the Barkhausen criteria, A beta equals to 1, we can derive the expression for the frequency. So here if I use the concept to calculate the frequency, where A beta equals to 1, we can derive this expression Fr, this is the resonant frequency, which is equals to 1 upon 2 pi R1C1 R2C2, and the calculation is very simple. Here R1 C1 are connected in series, so we can write R1 plus 1 upon j omega c, and these are connected in parallel, so we can write 1 upon R2 plus 1 upon j omega c, and just by calculating the value of Vf, which is equals to, suppose this is Z2 and this is Z1, so Vf will equals to V output into Z2 upon Z1 plus Z2, and if I calculate beta over here and put the value of A, if it is a non-inverting amplifier, the value of A will equals to 1 plus Rf by R input, and if it is non-inverting amplifier, the phase shift provided by this amplifier is 0 degree, and according to the Barkhausen criteria, the total phase shift either 0 or 360 degree. So if the amplifier is producing 0 degree of phase shift in the input signal, then using this feedback network, there is no need to add some additional feedback. So the feedback which is provided by the feedback network is again 0 degree. So the overall phase shift is 0 degree over the loop. So if we put for simplification, if R1 equals to R2 equals to R, then this frequency of oscillation can be represented by 1 upon 2 pi R into C. The Wien bridge oscillator can also be implemented using the BJT. So here this BJT transistor is used in place of op-amp. Op-amp is now replaced by BJT, and we know that the BJT amplifier provide 180 degree phase shifts. In the previous circuit, we have used the non-inverting configuration. That's why it is the phase shift of 180 degree, phase shift of 0 degree in the op-amp circuit. But in case of BJT, the phase shift is 180 degree. So here we need another 180 degree phase shift in the feedback loop. So total phase shift in this circuit, again it is Wien bridge oscillator using BJT, but here the total phase shift is 360 degree. So this is how we can implement the Wien bridge oscillator using BJT as well as using the operational amplifier. So in this class we have studied the concept of feedback, negative and positive, and oscillator definitely we use positive feedback. So without applying any input signal at the input to the oscillator, we can produce the sinusoidal output waveform at the output of the oscillator, simply using the Barkhausen criteria, which state that A beta should be equals to 1 and the phase shift over the loop should be equals to 0 or 360 degree. So the Wien bridge oscillator is very important oscillator of this unit. So this is all from my side. Thank you so much.